of us admirably stayed. There was like 5 people.
All right.
Yeah.
I think that's like cruel and unusual punishment going through a test without giving kids their scores.
Yeah.
It's like having your test graded in front
Well,
of you.
like she gives you the answers, so you're gonna try to figure out your score, but we didn't go over every question.
Gosh.
So it was like you just knew like how many you got wrong.
What are we doing there? There's a 50
No, it's lovely.
She said I did 100% below her other years, so we're just extra smart.
Should teach them like 1 minute.
What?
You guys ready? Let's get started. I'm going to do some drawings. You should probably do some drawings. All right, so let's talk about a satellite. I'm going to tell you guys about the most interesting thing today. I mean, I feel like it's fascinating. We're going to talk about a satellite first. So here's the Earth. Okay. Now we talk about satellites that are in like low Earth orbit. Like something like the International Space Station is in low Earth orbit, right? So here it is. And the International Space Station, what is the altitude of the International Space Station? Here, I'll ask my Google. Hey Siri, what is the altitude of the International Space Station?
One sec. The answer I found is 1,328,740 feet.
Because that's what I wanted to know was feet. Let's do this again. So, we know that I know, you know too, but I'll tell you. Okay, the radius of the Earth is 6.37 times 10 to the 6th meters. Okay, you guys got that? That's 6 million meters, 6,000 kilometers. Is that cool? All right. So the altitude, the height of the International Space Station, according to this, is 408. Now, if you're paying attention to the exponents, you're going to see one is times 10 to the 5th, the other is times 10 to the 6th, which means that when I look at this, so this is like 4, this would be like 63. Does that make sense? You guys with me on how the exponents here work? Okay? Oh, just a real quick aside, something that's kind of random, but I wanted to bring it up anyway. So, let's say this is the Earth. The mass of the Earth What? Should have just thrown it on the floor. Okay. So here's what I'm going to do. Times 10 to the 6, no, times 10 to the 24. 24 kilograms. Is it drugs? What are you doing here? Okay. So here's what I'm going to do. Ready? I'm going to take away everything except for one slice. % of the total. You don't have to write this part down. What is the mass of that slice? Okay? I took away 90% of the Earth's mass. I'm just left with this slice that's 10%. What do you think the mass is of that slice? 10% of the total. Yes?
5.98 times 10 to the 23rd.
5.98 times 10 to the 23rd? Is that true? Okay, that is a baffling idea. Like, that is 100% true, Thomas Carey. So the mass of this that's how big of a number this is. Like, it's hard for us to get a really good sense of this, of how big this really is. But when we took away 90% of it, it's still times 10 to the 23rd. Does that make sense? What is happening? If you think about all the people on the planet, this is an actual aside. If you think about all the people on the planet, let's say that people have a mass of about 60 kilograms. Is that cool? All right, average people have mass of about 60 kilograms. All right, so this is 6 times 10 to the 1, right? Guys with me on that? How many people on the planet? 7 billion? So I'm going to multiply this by 7 times 10. So 1,000 is 3, 1,000,000 is 6, 1,000,000,000 is 9. So I have 4.2 times 10 to the 11. That is the mass of all the people on the planet. Now, what does that mean? What this means is that this is the total mass of all the people. If you had, I want you to think about it this way. What if you had 1,000 of every person on the planet? 1,000 yous, 1,000 me's. We're going to take the population of the planet, we're going to increase, everybody gets 1,000. You get 1,000, and you get 1,000, and you get 1,000. What would happen to our number if all of a sudden we snapped our fingers, there was 1,000 extra people? What would happen to this number? Yeah?
10 to the 14.
Yeah, it would only be 4.2 times 10 to the 14. But look at it compared to this number. I mean, that's 10 to the 4, I mean, that's 1,000 of you. Let's say I did 1,000,000 of you, and 1,000,000 of you, and 1,000,000 of you. That'd still only be times 10 to the 17. You see what I'm saying here? Like, this is a huge number. This is a huge number compared to this number, which is the people on the planet. So, like, kids always ask, like, well, what if everybody just jumped at the same time? Literally nothing could possibly happen. Like, it's not even, the amount of people on the planet is so small. That was a quick aside. Let's get back to it. International space. Here it is. All right. It's in a nice circular orbit. I'm feeling really good about that. You guys good with that? I want to know, what is the G value at this altitude? what is the G value at that altitude? Okay? Is that something you guys think you can figure out? If you don't remember how to start, we're going to start with our basic principles, that the gravitational force, the small gravitational force, is also the large gravitational force, right? How do we calculate the small gravitational force? It's just mg. How do we calculate the large gravitational force? G, m1, m2, all divided by d squared. You with me on that? Is that cool? So then the question asks now, we're like, well, are any of these m's the same? Well, I think that this mass, right, because the International Space Station here is being pulled down. So this m and this m I think are the same. So if you want to calculate the G value, okay? Use your calculator. See if you can stab yourself in the finger last night twice in the same spot. So dumb. What's that? Well, it was the fact that it was late and I was using a knife not in its intended usage. I was very tired and not very focused. Do you guys remember the big G value? That's right. So here's the hard part about this. What's the D value here? Yeah,
The radius of the Earth plus the altitude.
good. So when we look at every one of these problems, when you go to calculate the gravitational force, the thing that goes in the denominator here is the center to center distance, right? So in this case, I think Luke was money in the bank here. He's like, look, it's not the radius of the Earth, it's the orbital radius. So in this case, it's the radius of the Earth plus the altitude height. Try to crank out value, please. Good value. Try to crank them out. It pays to practice, I promise. Okay? It pays to practice even just putting the numbers into a calculator. Good. So here's what's cool about this, is the G value at the International Space Station is about 8.7. And that would be meters per second squared, right? Could also be newtons per kilogram, that's fine with me. That seems like a weird thing, because what is the G value at the surface of the Earth? It's 9.8, right? Now, to be honest with you, this doesn't surprise me that much. Because the distance off the surface is a small amount compared to the distance from the center to there, right? Think about this. This is, we'll call this one, the total distance here would be like, we'll call it like 63, and then this one's like 67, right? It's just not that much farther. So the G value isn't that much smaller. But now we have a problem. We have a legit problem because have you ever seen video of astronauts inside the International Space Station?
Yes.
What are they doing? They're floating around. Now, the traditional middle school explanation is, well, why are the astronauts in the International Space Station floating around? Well, they're in space, and what do they tell you? There's no gravity in space. But you just told me that the gravitational field strength at the International Space Station height is 8.7 as opposed to 9.8. It's only like 10% less. So why, if there's no gravity in space, answer doesn't make any sense because look, there's a ton. Why does it look like they're floating around? Do you guys understand the question? Do you see why there's like a disconnect here? It's called cognitive conflict. I've seen them floating around. I always thought it's because there's no gravity. Clearly, there's lots of gravity. The gravitational field is only 10% less. Go ahead.
Does that have to do with something about the atmosphere and like the air around us letting us down? Or?
That is a great question. Does it have to do with the atmosphere around us pushing us down? So that is a classic. That is a classic question. I love that. The answer is no. Okay? But I'm going to highlight this with a couple stories. When I was younger and I was learning to teach physics, someone said this. They said, "Oh, you know what? If you go to the moon, there's no gravity on the moon." And I'm like, "What? What do you mean there's no gravity on the moon? Like, how could there be no gravity on the moon? Like, this doesn't make any sense to me." And they're like, "No, really, people think there's no gravity on the moon." I'm like, "How do people think there's no gravity on the moon?" Right? But then, I actually started asking people like, "Hey, what's up with the moon?" And they're like, "There's no gravity on the moon." And I'm like, "Why do you think there's no gravity on the moon?" And what people were doing is they were confusing the fact that there's no atmosphere on the moon with no gravity on the moon because they thought those two things were related to one another. Right? You see this? I'm like, "Have you seen pictures of astronauts bouncing around on the moon?" And they're like, "Yeah." I'm like, "Well, if you've seen pictures of astronauts bouncing around on the moon, how can you say there's no gravity on the moon?" Thinking, this is a perfect argument, right? This is like this, this thing is ironclad, right? And I'm like, so if there's no gravity on the moon, but you've seen astronauts bouncing around on the moon, how could that be? And their response was, "Oh, it's because they have heavy boots." I'm like, heavy boots? What the heck does heavy boots even mean? Okay, but you see there's some confusion here, okay? Then I was at a Michigan science teachers conference a couple years later, and I was still thinking about this, the fact that people like equate this like atmospheric understanding with gravity. Because I can see how this happens. Like your chemistry teacher will tell you, well, the air around you pushes on you with 22.4 pounds per square inch, right? The pounds is the force, the square inch is the area. So when we actually talk about that, that's a pressure. So pressure as a concept is defined as the force divided by the area. So they say the air around us pushes on us with 22.4 pounds for every square inch of area. That's what they tell us. The problem is that that's from every direction, right? If it were an actual thing, like then in the classroom, if I took my marker and I put it So there's more air below it than above it, it should go up. Does that make sense? Right? So I can understand where this is coming from. I just didn't think it was as pervasive as it is. So I'm listening to these two elementary school teachers talk. Actually, this elementary school teacher was telling other elementary school teachers about science. And she says, and I'm going to drop this ball, and why does it fall? And they're all like, gravity. And I was like, all right, I'll buy it. I'll let you buy into that for now. They're elementary school teachers. And she's like, and remember, gravity is the force of the air pushing the ball down. I was like, I'm sorry, excuse me? What? I couldn't even believe it. Like, you read about the fact that this is a common misconception, and then you see it, and I couldn't believe it. Okay? So it turns out that the air itself is not responsible. So, but this is a pervasive idea, and I'm glad you mentioned it. Like, oh, if I get above the atmosphere, that means there's no gravity. Turns out, that's not it. Okay? So let's go back. Why is it that the astronauts look like they don't look like they're floating around. They are floating around. Why? Go ahead.
Aren't they technically in free fall the entire time?
Technically in free fall? What were you going to say?
I was going to say that isn't the space station also being accelerated?
What are you going to say?
I was going to say that, I mean, like, I feel like although 8.7 is not a big reduction, it's still a reduction. Like, isn't it on the moon like 6 point something and they're floating around on the moon?
Well, they just bounce around on the moon.
Or they just completely float in space station?
Yes, they're floating. Yeah, you can even drive on the moon. There's like a rover that they drove around. It was really cool, right? So it's 1.6 on the moon.
Oh, it is?
Yeah, 1.6. 1.6. Okay. So I think you guys are keying into this pretty good. So how did we get this in orbit at all? Right? How did we get this space station in orbit? Well, we had to shoot it up off the surface, then turn it 90 degrees and start going around. Is that cool? Now, here's the thing. At any moment in time, okay? At any moment in time, if we were to look at it at various times, how many forces are on it? Just one. There's only one force on it, right? So which way is it being pulled? Inward toward the center, true? Is there anything to balance that force out? No, it's totally an unbalanced force, right? Well, if the force is unbalanced, then what does that tell you then? You are accelerating. So in a technical sense, you are always in free fall because you're falling toward the center of the earth. Think about it this way. I'll make an analogy, which is actually a good one. So you take your elevator up to the top floor, and here's you in the elevator, okay? And the cable breaks. If the cable breaks, what happens to you? Do you start falling instantly? Yeah. What about the elevator underneath you? Does it also start falling instantly? It totally does. What happens to you relative to the elevator cab then? Here's a question.